So we're starting today's lecture from here. Last class, not the last Friday, the last Tuesday, because we didn't have last Friday class. This is the part that we left off in our last class, that where we are trying to discuss the kinetic energy equation. This is something that we have seen, that how can we get the equation K equals to half mv square. And then we have this small discussion that work done against friction is that whenever any object will move as it keep on experiencing some friction, to achieve that movement, to achieve that motion, to achieve that displacement, we have to continuously work against that friction to overcome that effect and use the remaining force for the acceleration of the object. In that process, some amount of energy has to be spent, or some amount of work will always be converted into non-useful work, or in other forms of energy that we don't want, for example, heat and sound. This is called work done against friction. This is basically a loss, and the formula by which we calculate the work done against friction is very much same as the basic formula for work done, which is frictional force multiplied by the distance over which that motion was achieved. Beyond this point, what we have over here is the law of conservation of energy. This is actually a very important theorem for physics. Actually, it is for Newtonian mechanics. Newtonian mechanics means that for cases above the or bigger than the quantum physics level, I mean not subatomic cases, atoms and above, for our regular life scenarios that we see around us, this law holds true. Law of conservation of energy, you can see it over here. The statement is pretty simple. It says that energy cannot be created or destroyed. It can be only converted from one form to another form. So this would not be force. I think my handwriting was poor, so the student actually copied this wrong. Please correct it in your booklet as well. It can be only converted from one form. Form means one type of existence, one form to another. This is a given fact that whenever we'll convert energy from one available source and convert it into something else, we will always have to abide by this law for regular cases. Now, whenever I say regular cases, we have to understand that the irregular case or the unnatural case is the scenario where mass can be converted into energy, which happens for nuclear reactions. It is achievable from nuclear fission, which is breakdown, or nuclear fusion, which is merging. Fusion means merge. So apart from those cases of nuclear energy production, for all sorts of regular energy conversion that we experience, from chemical energy to other form of energy, or light to heat and electrical energy, if we rub our hands, the chemical energy in our cells convert to kinetic energy, and then kinetic energy by means of friction converts it to heat and sound. That heat energy, if we think further down the line, that heat energy can heat up some of the atmospheric molecules. As a result, the volume of that air which absorb that heat will become larger, so it will have less density. Then it is going to start floating above. Well, we will not be seeing that because air is practically colorless, but that's what's going to happen. So that rising of that air particles because of the less density will also be stored within that air particles as some portion to be kinetic energy because it's moving upwards, and also because it is gaining height against the gravitational force weight of the coming from the earth. So they'll be also gaining GP as well. So if you think about the whole process, we can eat some food which can give us chemical energy. Chemical energy is supplied to our muscles by the bloods and everything, so our muscles have the chemical energy. Whenever we move our hands one against each other, we convert the chemical into kinetic, and then the kinetic energy, because of the friction, converts into heat. That heat energy transferred to the air particles converts into the kinetic energy of the air particles and the gp of the air particles, because they're going to go up, so they're going to gain height and they're going to have some speed. So these are the type of scenarios that we have to consider in a lot of cases, which is going to be a large part of the practice for this chapter, work energy power. That whenever we talk about any physical process that involves energy conversion, we have to minutely understand each and every single in between form that in which through which the energy conversion is happening. This might sound a bit complicated, but I assure you it will not be complicated as long as you understand what is happening. There are few things. I mean, what I'm now currently discussing is a bit that is not related to this part. I think this is somewhere over here. Hold up. Energy conversion process. Now here we search. Okay, so yeah, this part that I'm talking about is not apparently in the notes, but we have some example for this chapter in the IGCC book. So I'm going to get into that part as well. But hear me out at this point. It's important that you understand what I'm trying to say. Whenever you are trying to describe the energy conversion of any relevant process, it is really important that you try to think that what are the type of energy conversions that will happen simultaneously, and what conversion will happen consecutively. This is very important. Simultaneously and consecutively. Simultaneously means that what are the type of energy form which will be produced side by side, and then one of those energy form could be converted into something else. So that's a different thing. If I give a bit of an example, try to think about it, that let's say if we are if we have if we are trying to light up a filament lamp using a battery by electricity, then what is the type of energy conversion are we talking about? First, in the cell, we have chemical energy stored because of the chemical bonds of the electrolytes which are placed inside the battery. Be it rechargeable battery or it's a one-time battery, doesn't matter. The energy stored within a battery is always in the chemical energy form, which is the chemical energy of the electrolyte molecules. Whenever we close the circuit using the filament lamp, we allows a continuous chemical reaction which converts that chemical energy into electrical energy. Electrical energy is the type of energy that we can achieve when charged particles move from one place to another place. Charged particles moving doesn't necessarily mean electrons moving. It can also mean positive ions moving through a certain electrolytic solution as well. So in any case, whenever there is flow of charged particles, we can call it current, or that is what we define as electrical energy. The movement of charged particles is defined to be the availability of electrical energy. So first we have chemical reaction, which converts chemical energy of the electrolytes in the battery into electrical energy. This electrical energy is converted into the filament, which is the very thin wire which is coiled within a very small space, the part that glows in a filament lamp. This electrical energy, as it flows through the thin wire of the filament of the lamp, it converts into light and heat energy simultaneously. This is the key part. You have to understand this thing. As electrical energy passes through the filament lamp, or charges passes through the filament lamp, its electrical energy, the energy carried on by the charged particles, it converts into light and heat simultaneously from the coil. But it's not usually, I mean, if you think about it, I mean, whenever the light is glowing at regular brightness, you have both of this output happening simultaneously. It's not that first it produces the heat, then the heat converts into light. It's usually not like that. So if you try to think about in terms of, if you try to write it in a block diagram or in a set of block diagram, it can be that you can write chemical energy in a single block, rectangular block, arrow, electrical energy. So chemical converts to electrical, and there is no subsidiary product along with electrical. So electrical energy is a single box. Then you give another arrow. Then in the third box, you have to write heat plus light simultaneously. You cannot write heat into arrow light, or you cannot write light arrow heat, because that would mean that first you have heat, then you have light, or it could mean that first you have light, then you have heat, but that's not the case. You have both the heat energy and the light energy produced simultaneously out of this process. That, and then that is the output form of the light source of a filament lamp. And then this energy is dissipated out into the atmosphere. It can be radiated. Some amount of energy gets convected because of the atmosphere. So then this energy is actually dissipated out from the light bulb, and it can be going someplace else. It will not be destroyed. It will be absorbed by something else, converted into some other form, dissipate out. So those things will happen. So this is just one example for me to give you the idea that what do you mean by simultaneous conversion of energies. This is really, really important that you understand the significance that happening the energy conversion happening one at a time and energy conversion happening simultaneously is different. You have to be careful about whenever you write about those things, to be whether you're going to write in individual arrows or you're going to write two forms with plus sign, two forms written in plus signs, that heat plus sound or heat plus light means that they were produced simultaneously. Similarly, the first example that I was talking about a bit earlier, that if I rub two of my hands together, first I have chemical energy in my muscles, which converts into kinetic energy of the hand. So first, chemical energy converts into kinetic energy because I'm actually moving. Then friction converts that kinetic energy into heat and sound simultaneously. So you have a simultaneous production of heat and sound as you rub your hands together. Your hand is becoming hot and it is also producing sound at the same time. It's not that one produces before other. So this is quite important. To be honest, there is no practical limit for how many of these energy conversions I should be discussing with you, because in our regular life, if you just look around and use a little bit of a physics understanding, there are hundreds of examples of energy conversion that is happening around us. So any question can come from any of these parts. So it's practically impossible or impragmatic to attempt to discuss all of them. But as long as you get the idea, it's easier for you to go ahead with that process. Another example that I'd like to discuss very minutely, which is the most common type of energy conversion that we human beings as a species very much like to have. Energy is available in a lot of different forms. We have a lot of different forms of energy. Actually, I think I shared one of those book printout with you, PDF with you last class. I'm gonna find this up just a second. I think it's somewhere over here. Yep, I was talking about this one. So this is actually a small PDF that I shared with you the last class that we have had, and it has some pretty good discussion for what kind of energies do we have available and so on and so forth. Exactly. This is the block diagram that I would like to discuss with you. There are two primary difference between these block diagrams. Here we have only one of them, actually, because they actually emphasized on one of them. This is actually a schematic figure for how does an actual power generation unit or power plant actually looks like. It has a lot of stuffs, and these are the turbines which rotate under the effect of very high pressure. So these are the superheated steam. These are the slightly cooled off regular steam. And we have multiple of these stages. All of these things convert the heat energy into kinetic energy of the rotor. This common shaft that you can see that runs along this entire thing. So these parts, I mean, up to where you can see these pipes, these are the pipes which feed the superheated or extremely hot steam onto these turbines. These are like blades. And the reason they have this kind of conical shapes, because as the steam energy gives up a part of their energy to one set of blades, they become cooler. So they don't have that much energy left to actually provide further energy. So they need a bigger expansion size to provide good work. So there is a pressure gradient from the center part to the outer sides. So that's why we need this kind of conical shapes. However, that's not very important for you to understand. But what goes to the saying that this is this part where you can see the pipes. I mean, the part where I'm moving my mouse around. 1, 2, 3, and 4. These are the 4 parts where we feed hot steam, and that hot steam converts into kinetic energy by the rotation of the turbine. This turbine in turn rotates a coil of wire which is inside the generator. So this shaft, this cylindrical shaft that you can see, that is this one that runs along this entire thing. So this shaft takes the kinetic energy out of the heat energy from the steam, and then it rotates a coil in this generator where we have electricity produced. The point I was trying to get at is that we human beings as a species, our most favorite form of energy is the electrical energy. And there is a reason for this. The primary reason is that out of all the form of energies that we have come across, as far as our researches and discoveries go, electrical energy happens to be the form of energy. Electrical energy happens to be the form of energy that is really easy to transfer from one location to another location. I mean, I'm not saying it is the most efficient. I'm saying it is the most easy to transfer for an earthly environment, to transfer from one location to another location, compared to other forms of energy. For example, light energy, heat energy, mechanical energy like GP or K, or sound energy. I mean, or even chemical energy. You can have all different types of energy, but among all of those energy forms, transferring electrical energy from one place to another place happens to be the most easy, because we can essentially produce a lot of metallic wires, and metals are quite available in earth, on earth's crust. We can mine them pretty easily. Metals are good conductors of electricity, so they provide low resistance, so energy can pass through metals with experiencing pretty small amount of resistance, which means that we are not going to lose a lot of amount of energy. And basically, using all those wired networks, we can transfer electrical energy from one place to another place pretty easily. It's not very difficult. And it's not very difficult in a comparison. Comparison means that if you try to think of how can we possibly, I mean, if we wanted not to transfer, let's say, electrical energy from one place to another place, if we wanted to transfer, let's say, other forms of energy, let's say, in all the houses and all the factories and all the offices, we're not going to transfer heat energy, or we're not going to transfer electrical energy, rather we're going to transfer mechanical energy, which means there would exist a certain power plant where we'll have some large shaft rotating by some turbine, and this moving thing would be chained or linked with multiple things, and that should travel to all the individual houses and offices, buildings, and there'll be rotary parts available to all of us so that we would have access to kinetic energy. It's difficult to even visualize because that's so much construction that you have to think about. Compared to if you think for electrical installation, it's pretty simple. You just have hidden wires inside your walls and you just press the switch and stuff starts working. You don't even have to bother about the installation process or what they are, because they don't need maintenance. It's a very important thing, that anything that you construct, anything that you erect out of nothingness, you have to think about it. It's long-term service. If you have to repair it every once in a while, it's not a very good design. It's not a very good way to do that job. Well, if you cannot do without, then it's a different thing. There are certain things that we design. There are certain things which is for which things are purposed for doing destruction, or doing or getting attention. For example, one of the examples that I can give that uh, the purpose of a towel is to get wet, or the purpose of a duster is to become dusty. So we have to clean it every once in a while. It's the purpose of this thing, but that's not applicable for energy transfer processes. So we have to have a way to transfer energy efficiently that would require less attention and less repair over the process of over the duration of time for usage. And equally applicable for if you think for other type of energy. For example, if we want to transfer heat energy from one place to another place, it's very difficult, because heat energy can transfer from one place to another place in 3 different ways, which you're gonna see them in detail in the heat chapters. But apparently the most efficient way by which we can transfer heat energy from one place to another place is by which heat energy is transferred in the universe, basically in the form of electromagnetic radiation or infrared radiation, by which we receive the heat energy from the sun. It just continuously shooting out heat energy, and we receive the infrared energy, which is the radiation form of heat energy. That works good as long as you can make this happen in vacuum. But Earth is practically not vacuum. It is a solid liquid surface with wrapped around gaseous material. So we cannot essentially have very efficient radiation process through a physical medium. Even if it's gaseous medium, it does obstruct radiation by a significant amount. And one of the problem is that, I mean, if we want to transfer heat energy from one place to another place other than electrical energy, it would be very difficult for us to actually supply the produced amount of heat to the hot location. For example, let's say my house is, just for the sake of example, let's say there is a power station which is supposed to supply me heat energy, and my house is 10 kilometers away from that factory, from the power station. 10 kilometers is actually pretty short. It's not pragmatic, but let's consider this as an example. If they have to sell heat energy to me, then hot objects or heat energy should be transferred from their production site to my house by some means. So it has to be reached, it has to reach my location, and I have to receive that heat energy. In the process of transferring this energy over these 10 kilometers, no matter how you think about it, whether you transfer it by solid material, liquid material, gaseous material, pipeline, you would have to think about a very bulky amount of insulation around that channel, so that you do not lose that heat to the surrounding. Because you have to understand one thing, that heat is such a form of energy that it will always travel from hot objects to cold objects. By using insulation or by using lagging material, lagging means something that actually reduces the heat loss, that stops the convection, or radiation processes. Basically, it's an obstruction towards heat transfer. By using insulation, we can reduce the amount of rate of heat loss, but we can essentially stop it. It's impossible to stop heat loss whenever you have a hot object that is in contact, or that can potentially come in contact with a cold object. So that's a given. That will always work. So it's not very pragmatic to supply heat energy as well. The reason I'm telling you all of these different forms, so that you can essentially, so you can try to think about that. Why is it that we are so much interested in electrical energy? Why is it so important that we want to convert all forms of energy into electrical energy? The only reason is that it is very easy to transfer electrical energy. Now you guys might think that, well, there are places in the world where we don't have electrical energy. How about them? Well, in places where we don't have electrical energy, typically what we do is we carry liquid oil in large barrels or tanks to those places, and then we can use that thing for our purpose, for our energy requirement. Carrying chemical energy from one place to another place is not as easy as supplying electrical energy. Once you have an electrical line, you don't have to bother about your car. You just have long poles with metal wires. There is no moving parts. So there is very less possibility for repair, unless you have physical damage or lightning or those kind of natural disasters. So we can transfer a significant amount of chemical energy in terms of fuel, oil or gas or coal, for example, solid fuel, from one place to another place. That's possible, but it's not as easy as transferring electrical energy. So it is, if you want to continuously supply electrical energy, then it is better to have the electrical installation, the grid that we call, use the word grid. Grid means the network of wires by which you can transfer electrical energy to distant corners of your location, of your country or your state or your land, to the people. So this is the reason that in the next upcoming part of the lecture, we're going to talk about that how can we convert all the different type of available energy resources, be it a renewable energy resource or a non-renewable energy resource. How can we convert them into electrical energy? Because any location or any place that can give us some form of energy resource as a source, we would primarily want to find a logical way to convert that into electrical energy. Because if we can convert it into electrical energy, we can very easily sell it to people, or we can at least very easily transfer it to the locations where they are meant to be used. Sorry, just a second. Hello. Sorry, I was coughing and so I muted channel. Can you please hear me right?
Yes, sir.
Okay. So in from different locations, we can have different form of available energy, and it is our interest that how can we convert that available form of energy uh, to electrical energy. That's something that we want to achieve. That's something that we want to have. And this can be primarily done in two ways. Two ways means there are certain, although very few, there are certain type of energy resources where we can convert the available form of energy without converting it into heat. Let me elaborate for you. For example, if you try to think about it, let's say if we find in a certain geographic location some gas, for example, Bangladesh has a lot of gas oils wells. So if we in some place, if we find some gas, we can take that gas. The way you can liberate that chemical energy in the gas is to burn it. The moment you burn it, you are liberating heat energy. Equally applicable for coal, equally applicable for mineral oil, equally applicable for nuclear fission, where we actually break down nuclear fuel of large unstable nuclei into smaller daughter products, and we can liberate heat energy out of it. Or we can have other sources where we can directly get heat energy. For example, if you think for geothermal locations where the earth crust is thin enough that the hot stuffs under the earth crust, the magma. There's one thing that I would like to give you a bit of a distinction, that the molten stuff underground, as long as it is kept underground, is called magma. The molten stuff underground, whenever it is erupted out, is called lava, as long as it is in liquid form and flowing on the surface. when it becomes solid once again after cooling off enough, it's called igneous rock. So these are the name differences. So inside the ground, still liquid, magma. Outside the ground, erupted through a hole and still liquid flowing, lava, became solid, rock. So there are certain locations in the world where where the earth crust is thin enough, or the locations are where where it is accessible, that the stored heat underneath inside the earth at the core of the earth, that heat can be readily made to be available. So the earth actually gives up some part of its heat through those locations pretty often. So we can have geysers. Geysers are basically some sort of trapped pressure cooker kind of stuffs, where we can heat up a lot of water that is boiled from the subsurface heating, and that steam gets locked up in a location, and whenever there is enough steam, pretty much like a pressure cooker, it shoots up that steam at a pretty high pressure. So that steam, if we can capture that steam and eventually can convert that into electrical generation, we can do that. In some locations, it might not be as hot to actually uh, it might not be as hot naturally to actually boil the water, but we might as well get hot enough water, for example, hot springs and such, where the temperature of the water could as well be, let's say, 50 degrees, 60 degrees, 70 degrees, but not, let's say, if it is not about, close to 100 degrees Celsius. There are ways by which we can concentrate heat energy. So you can take a large amount of lower temperature, and there are ways by which we can actually concentrate the heat energy. Uh, there are mechanisms for that. I'm not getting into that thermodynamics discussion, but we can do that. We human beings have devised a way that we can extract a lot amount of heat energy from cold objects, apparently cold objects, and we can concentrate that heat energy to give rise to a much higher amount of temperature. It's possible by some mechanism that we human beings have developed. So in those locations, the basic readily available form of energy is heat. So that's another thing. The other type of heat energy that we can make available, which is also possible to achieve in pretty much everywhere in the world, except for some coordinates too close to the pole, we can have solar thermal plants. Solar thermal plants are something like that. Uh, if you can somehow absorb the heat energy of the sun in an efficient way. Now, the word efficient is the key here. I mean, sun's heat, heat is falling on the earth every day, like every day, 365 days a year, to at least, let's say, on average 12 hours 12 hours a day, we're receiving those heat and light energy. To be able to utilize that heat energy, we have to somehow be able to capture that heat energy and be able to capture it efficiently and concentrated form, so that we can use it for other purposes. So there are different designs for it. I might as well actually show you some examples. There are some very amazing videos for what kind of solar thermal plants we can talk about. We can have Savannah power plants, we can have convection plants, we can have radial axial plants. These designs are beautiful. But my point is that if we can capture that heat energy that is directly available from the sun, we can also use that heat energy to convert that into electricity. These are, so I'm trying to make a distinction line that there are certain type of energy resources. There are certain type of energy resources where either the heat itself is the very basic available form, for example, geothermal or the solar thermal, or they are the primarily available energy resource is not heat, but if we want to use that energy form, the very next that we first have to convert it into heat. For example, chemical energy in the fossil fuel or nuclear energy in the nuclear fuel. If you want to capture that energy for your purpose, you have to first convert that into heat, and only from that heat energy can you start converting into other forms. So for these kind of energy resources where heat is a very basic starting product or second starting product, the process is pretty simple. We take that heat, we boil some water using that heat in a pressure cooker type of container, which is called a boiler, industrial device. And in the process of boiling, the water molecules convert into steam and they carry that heat energy. And then we blow that hot steam like a nozzle or a hose pipe onto turbines. Turbines are basically inverted propellers, and those things rotate the turbine. So in that process of blowing, the heat energy of the steam molecules convert into kinetic energy of the turbine. So in the process, in the turbine is the device. Turbine, if I go step by step, boiler is the device which converts the uh, which practically transfers the heat energy to the water. So if you have initially, let's say, chemical energy in terms of fossil fuel, coal, gas, or oil, so we burn that thing underneath the boiler. Boiler is basically a very large pressure cooker. Think about a pressure cooker, and let's say make it 5-story tall and proportionately wide. That's basically a boiler. So you have a lot of heat going in, and a huge amount of water is boiling every second, and you're producing tons of steam every second, and you are taking them through a pipe into some other location. And these are those pipes. Actually, in this case, these horizontal tanks that you can see over here, these are the boiler tanks. There are different ways by which they are boiling. So, but they're producing the steam, and then those steams are actually sent into the turbine. So these black things are the turbine. Turbine is the device. So boiler is the device which primarily converts chemical energy into heat energy. Then turbine is the device which converts the heat energy into kinetic energy, because that's where the shaft starts rotating. So turbine converts heat into kinetic energy, and then this kinetic energy is fed directly to the generator. Generator, or sometimes it is also called an alternator. The reason we call it is sometimes called an alternator because most of the generators that we use around the world, let's say about 95% or 95% plus, most of the generators that we use around the world, they all produce AC, alternating current. Now, AC and DC are two different type of current, alternating current or direct current. We can talk about them in chapter. So sometimes generators are in generally also called alternators. Alternators means that which produces alternating current. All alternators are generators, but all generators are not alternators, because generators can produce DC or AC both. DC or AC either, not both. DC or AC either, depending on their design, depending on how we have designed them. But alternators are those which exclusively produce AC current, and most of the generators produce AC current. So sometimes generators are also called alternators. So because they are very common. So for example, let's say, let's not get into that example. Sorry, my bad. So generator is the device, or alternator is the device which takes in the kinetic energy and converts the kinetic energy into electrical output. So I'm just trying to really give you the name of the three devices which takes one form and converts into other form. Boiler, we input boiler chemical energy, it converts that energy into heat energy. Turbine takes input the heat energy, produces kinetic energy. Generator takes input the kinetic energy, produces electrical energy. So this is the sequence of energy transfer that every power station which handles heat energy works by. So this is a very basic process. That any single case we have availability of heat energy, we'll immediately boil water. We'll produce steam. Steam will be flown into turbine. Turbine will be rotating the shaft, coil, and the coil will be producing electricity. This is one type of way. There are certain few other type of energy resources in which we do not have to boil some water. So this is the part what I need you to understand. I don't see that good table over here. There a block diagram would have been much good. I don't see the block diagram over here. Do we have a block diagram in here? I hope we do. We don't. No, we don't. আচ্ছা, এখানে তো আমাদের আবার শুরু হয়ে গেছে, কি বলে, ডেনসিটি প্রেসার শুরু হয়ে গেছে। আচ্ছা, নেভার মাইন্ড। I'll try to show you the block diagram. You kids can drop this block diagram in any of the blank spaces that you have in your notes, or if you don't want to draw it up over here, if you want to draw it somewhere else in your personal paper, you can also do that. So let me just show you some small examples, rough drawings. So কথা বুঝা না গেলে, or if you need me to repeat or slow down, please let me know that so that I can do that accordingly. She should do, I believe. So this is boiler, this is turbine, this is generator. In the boiler, we provide chemical energy, which converts into heat energy in this place. Turbine produces kinetic energy output. K is the short form for kinetic energy, so don't write KE energy. KE, it means kinetic energy. And the generator produces the output, which is electrical energy. So এই হচ্ছে basic energy production process in which we means we human species, we typically produce electrical energy. To produce electrical energy, this is the endpoint output. So whenever there is heat involved, there will always come a boiler, and the boiler will take the heat and eventually make steam, produce steam, and this will happen, which I've been discussing quite a few times earlier. There are certain other cases where we can avoid the heat energy. For example, one of those cases is called the hydroelectric power plants. Hydroelectric power plants. The idea of hydroelectric power plants is very simple. Let me show you a very simple figure, which I believe we have in this book diagram. This is actually this one. I think this is Hoover Dam. I'm not sure. I think this is Hoover Dam. But yeah, this is basically how our dam looks like. So what is actually happening over here? If you have a look at this figure, it's not very vivid, but should be able to make sense. So naturally, there was a river that was flowing from this lake. So, or maybe this is the original flow of the river, and we took a portion of this water into a certain ground, and normally this water would be flowing down through this stream naturally. What we did is that in the closest part where we have lands pretty close to each other, we made a dam. So this is a man-made structure which is actually storing up a lot of water. As the water level will rise, it will store GPE. What we'll do eventually, when there is enough water over here, we are going to allow controlled flow of water through this tank, through certain pipes which will be located over here. And these structures that you can see over here, these are usually the powerhouses, which means through some pipe, water is going to flow down. As water will flow down, GP will be converting into K, and we'll convert, and then we'll directly use that flowing water, because in this case we are talking about water that is already flowing. So we have availability of kinetic energy. So we directly have kinetic energy available, which means because we already have kinetic energy available, we practically don't need the boiler. So there will be flowing water like this. There'll be flowing water like, let's say there'll be flowing water like this. In this flowing water pathway, we're going to place up a turbine. So let's say this is going to have a lot of blades. So we're going to flow this water over here. This is actually one beautiful rough image in the worksheet, I believe. If you have a look over here. Yeah, something like this. So we have a water jet coming in. we're going to hold up this turbine over here. We need the turbine because uh, turbine essentially will convert this linear kinetic energy. I'm using the word linear because this is a kinetic energy that is available, that is flowing in one single direction. Whenever it will hit the blades of the turbine, this will convert that linear kinetic energy into rotational kinetic energy. So this will cause this shaft, this black line, to rotate, and that rotation will eventually rotate the coil that is inside the generator, which is not drawn over here for the sake of simplicity, and then which will be converted into electrical energy later on, which means basically we're going to need only this segment. Let me draw a bit of a line. Let's say we're going to only need this segment. We're not going to need the boiler anymore for a hydroelectric power plant. We're going to need the turbine, and then we're going to need the generator. So in that case, heating up water and boiling up water into steam is not necessary because heat was not an intermittent form. Heat was not involved. We had GP of the water stored in the dam. As water flows down, it converts into kinetic energy. We flow that water into the turbine. Turbine transfers the kinetic energy to the generator, and the generator converts the kinetic energy into electrical energy, and that's that. So this is one type of form that we can have. The other example where we do not have to take have to handle with heat energy is photovoltaic cells. This is actually a word. I'm going to write this word. It's a mouthful, bit mouthful. Oops, where is the pen? There you are. The word is this: photovoltaic. Photovoltaic means, photo means light, voltaic means electricity. So photovoltaics mean that it is the study of stuffs where you can produce electrical energy, voltage, by means of light. So basically what I'm talking about is what you have seen for small scale structure in your calculators. You have a solar cell. uh, the solar cell actually helps for the longevity of the battery, because whenever there is enough light around, you can essentially get your calculator running from the solar cell. And if there is not enough light, you are working in a comparatively less bright situation, then the battery will provide the energy. These solar cells are not, in your calculators, are not designed to charge up your battery, because the battery that you have in your calculators, they are not rechargeable. For as far as I know, most calculators work with non.
Sir,
Yes.
I'm sorry, could you repeat what photovoltaic is?
Yes, sir.
Photovoltaic is the study, or is the type of science where we produce volt from photo. Photo means light, and volt essentially mean electricity. So the section of science which handles of production of electrical energy directly from light energy. বুঝছো?
Yes.
আচ্ছা. So that's the photovoltaics. So photovoltaic cells, or if you can only write solar cells, they both mean the same thing. uh, Photovoltaic cells are also sometimes called in short PV cells, which can also have, basically there's the solar panels. So in those type of energy conversion, the available form of energy is the light energy directly from the sun. And using photovoltaic cells or solar cells, we can directly convert the light into electricity. We don't have to bother for any steam, any turbine, any generator, nothing. Only those flat panels can directly convert the light energy into electrical energy, and that's that. So ওইখানে আমাদের কোনো রকম মুভিং পার্টস লাগবে না. We don't need any of this boiler, or nothing is required, even not even the generator. Those photovoltaic cells, they will feed on the light available from the sun and directly convert it into electrical energy. So that's another type of energy resources that we can have. Important point is that one of the one of the important point to consider is that any factory or any plant or any production facility, the fewer number of moving parts you can design into a machine, the longer it is likely to survive. What I mean is that if you think about, let's say, any device that has moving parts, whenever you have moving parts means that anything that has relative motion with respect to each other. For example, in a car, there are a lot of moving parts: pistons, shafts, and then the crankshafts, camshafts, levers, and the wheel rod, and there are a lot of moving parts. Whenever we have moving parts, there is likelihood of friction. Friction will produce heat, and it will also do tear and wear of the material. So you'll have misalignment, so which will lead to requirement for repairing or replacement of equipments if they become really unusable. The fewer number of moving part a certain machine can have, the less maintenance is going to need. And the beauty of photovoltaic cells is that it does not have any moving part whatsoever. It's just a basic panel where there is some magic in this panel. So that magic is something else. We use semiconductor materials and their special properties of ionization energy, or is what is this thing called, work function value. These are some technical terms. So we can design, this is just a simple piece of panel of object. There is no moving parts. The electrons of those inside those things, those are the things that move. So electrons are going to move anyway, which we cannot control, and that's not a problem. So they don't have any moving parts. So ideally speaking, if a set of a solar panel farm is not destroyed by some natural occurring phenomenon, or it's not it's able to withstand the variation of weather. Variation of weather means that sometimes it's winter is pretty cold, sometimes it's summer is pretty hot. If these things are designed to withstand the change of the weather, theoretically these photovoltaic cells should be able to convert light energy into heat energy forever, because they don't have any moving parts. So they are very less likely to become unusable, very less likely. Over the duration, it might be possible that their material might become degraded, or they might not have that much efficiency, but they are not supposed to become altogether non-useful or altogether destroyed. It's unlikely, quite unlikely. Why am I telling you this? Because efficiency is a very important factor for any type of energy conversion. Efficiency, essentially, there is a definition for efficiency over here. Many of you might know this already. I'm just going to show you from here that efficiency is this thing. Efficiency, this is actually wrong. This is not electricity. This was supposed to be efficiency. So I'm pretty sure it was my poor handwriting, which the student actually copied wrong. So please cut this off and correct this in your notes as efficiency. This heading is supposed to be efficiency. Here it is correct. So this should be also efficiency. The definition of efficiency goes like ratio of useful output energy or power. Double slashes mean power. It does not, because sometimes a single slash could mean division. So to avoid the confusion, yeah, double slash means oblique. It's an exclusively means or. So ratio of useful output energy or power and total input energy or power. It means that we can say that the efficiency can be said as the ratio of work by work, or it can be said by the ratio of energy by energy, or it can be said by the ratio of power by power. Just to elaborate this idea, I wrote these three different equations over here. So useful output work divided by total input work, useful output energy divided by total input energy, useful output power divided by total input power. So what is the meaning of this useful and what is the meaning of this total? I'm going to give you a bit of a discussion for that, which is upcoming. But efficiency is a very important term whenever we are talking about process of energy conversion. We want our expected form of energy to be available out of an energy conversion process. For example, now that I'm talking into a microphone, the aim for my my aim as to go ahead for the lecture is that my vocal cords should just vibrate enough so that I can make you kids hear my lecture. That's it. So I'm not going to scream, because that will be wasted of energy, because I'm not physically taking a class. I'm just talking into a microphone. If I ever sense that my volume is not good enough, I can try to increase the input volume of the microphone, or I can try to bring the microphone really close to my mouth, for example right now. So that can also be achieved. So what I'm going to do is that I'm going to try to use the least amount of resource to get the most benefit out of it. That's what efficiency is all about. That we want to have the most amount of useful form. Now, this term useful can be confusing sometimes, because this is the key term which actually defines the term efficiency. That what is the meaning of this term useful energy? I mean, we are doing some energy conversion, so what does it mean as useful energy? It's actually pretty simple. If I try to give you a bit of an idea, for example, for a power station, let me give you some idea. Let's say we take some, let's say we have a thermal power station. Thermal power station means a power station which essentially works by producing heat or burning fossil fuel. They are called thermal power stations. Let's say we have a thermal power station which burns some chemical energy and converts it into heat, and blah 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 stuffs happen. Let's say, just to make sense with you, we are going to start a certain heat energy conversion process with, let's say, 100 joule of chemical energy. We're going to burn this thing in the boiler. Now, what I want to think, in the process of burning in the boiler, our aim is to boil water. That is our aim, which means we are going to liberate chemical energy from the molecular bonds of the fossil fuel, and we want that energy to be transferred into the water molecules. That is what our aim is. That is what useful means for the boiler process. But there is a catch. We cannot do that altogether. The reason we cannot do that, that whenever we will burn, the boiler will always give up some exhaust, because you have to let those burned carbon dioxide and H2O molecules out from your boiler burning container. That air or that mixture of gas which is going to leave out of your boiler will always be hot, which means out of this 100 joule, some amount of energy will be leaving as exhaust. You cannot use all this exhaust amount of energy into the water. You cannot send this. You can design it to be pretty small, but you cannot make it zero. Some energy will always be wasted going out through your exhaust. That's one source of your loss. Another thing is that if you're trying to boil up some water, your aim is to transfer the heat energy produced from the burning of the fuel to transfer it into water. But the limitation is that you cannot transfer that energy to the water without first heating up the boiler tank. So which is very simple. Let's say you're trying to heat up even in your kitchen, if you're trying to boil some water, you first pour that water into some cooking pot, put it on the fire, and then the pot heats up, then the heat is transferred to the water, and then the water starts to boil. To make the water boil, you have to make the pot hot. But it was not your aim to make the pot warm or to make the pot hot. You had to make the cooking pot hot enough so that the water would boil. So to make the water boil, you had to make it happen even though that was not your intention. Which means the amount of heat energy that you are using to heat up the cooking pot, or let's say heat up the boiler container, that heat is not being transferred to the water. That heat is being absorbed by the cooking vessel. So that heat is also wasted, because you could not place it in the location that it could possibly go, which means we have some wastage. I'm giving minus sign, or I can give a single minus sign. I can add up all these things. Some heat is being lost as the exhaust, some heat is being absorbed by the container. So I'm only going to write container, which can be the boiler container, which can be the cooking pot. So container is a general term. So let's say this is a container. So you are going to lose heat energy. Definitely you're going to lose heat energy by these two processes. The other thing that is important, that so this is what is going to essentially happen in the boiler. So we cannot transfer all of this. Let's say, just for the sake of discussion, let's say we are going to be able to transfer, let's say altogether in a well-designed system, let's say we're going to lose only 10 joule of energy out of these processes, which means 90 joule could be transferred to the steam. So now the 90 joule of steam is coming to the turbine. Now the turbine is going to start to rotate. Now, in the process, when the boiler is going to feed the energy to the turbine, once again, you cannot transfer all of this energy to the turbine. Let me show you why. Have a look. If you have a look at this figure, of this of a typical power station, this is how a turbine looks like. All of this, these are this is a Pelton wheel. I think this is, yeah, these are Pelton wheels. We send the water over here, which these are curved surfaces, and yeah, this is actually a very nice Pelton wheel. Yep. Yeah. If you think about it, have a look. These are our boiler stuffs, boiler container. And we have to take the steams out of here, and immediately we have to flow through them through pipes and input those steam in appropriate location of the turbine. As the steams will flow through these pipes, they are gonna lose some heat to the atmosphere. We can apply lagging or insulation around these pipes, which can reduce the heat loss, but you cannot make it zero, which means some heat is also lost to the surrounding. Then as you're gonna send in the steam over here, all the steam would not be coming down to room temperature water. I mean, what could we possibly think to be perfectly efficient heat transfer? Have a look. Whenever we try to understand, let's say we liberated 100 joule of chemical energy. We converted 100 joule of chemical energy to begin with and converted into heat energy. Then we want this heat energy, I mean, what is our expectation? That a best process, a perfect process should be able to convert this 100 joule of chemical energy into 100 joule of electrical energy. This is a process that we can say to be 100% efficient. That the total input energy is equal to total output energy, which means there was no loss. This is what we want to achieve, but it is difficult to achieve, or in some other words, it is impossible to achieve. So in this case, we have some losses, and the other type of loss that we can have, that whenever, think about the inherent process of boiling water. Try to understand. If you are trying to boil some water, what is essentially true that first the water, I'm just showing you a small beaker. Let's say this is water. This is room temperature water. So this is 25 degrees Celsius. If you want to boil this water, you have to heat it up from 25 degrees Celsius to 100 degrees Celsius. Then by adding additional heat, you have to convert that 100 degrees Celsius water into 100 degrees Celsius steam. So this is water, this is steam, state change. And then maybe you can add up more heat to eventually increase the temperature of the steam even further. That's also possible. So you have to provide heat through this entire process of heating and state change. Why did you provide this heat to the water? Because you wanted this water to be your carrying medium of heat energy to the turbine, so that the turbine could rotate. So the turbine would have been able to extract all of this absorbed energy if it so happened that, let's say I'm going to give a value over. Let's say this is 120 degrees Celsius steam. I'm just giving a value so that I don't have to talk about in guessed terms. Let's say this is a turbine house. This is going to take input 120 degrees Celsius of steam. Nice and easy. If this turbine, after absorbing heat energy from the steam, could give out water at 25 degrees Celsius, then we could have said that all the heat that this water absorbed in this process, turbine could absorb all of its energy. But that doesn't happen. The turbine cannot ever convert that steam into liquid water. The turbines are essentially designed to operate at only gaseous stage of water, which means it can only operate with steam, which means this turbine might as well, let's say at best, it can give out this material, this 120 degrees Celsius. At best it can do is that it can reduce the temperature, it can absorb enough heat so that this output is actually 100 degrees Celsius steam. That's the best it can do. A turbine is not designed, no turbine is actually designed to absorb, to work in two different state of the substance. So it can either, if it is designed to work with liquid water, it will work with liquid water, period. If it is designed to work with steam, it will work with steam. Which means, by no means, can this turbine actually absorb all the heat that was supplied in this process? It could only absorb, or it could only extract out from the steam a certain fraction of the heat energy that the steam brought into the turbine. It cannot extract all of the energy, because if it could, then the output material would have become 25 degrees Celsius water, room temperature water. But that's not the case ever. It doesn't happen. Which means whenever this hot steam is actually leaving out from the turbine, I'm going to name this turbine. Essentially, this leaving material is also leaving out with some amount of heat energy, which we could not extract, which we could not get our hands on, which we could not keep for converting to the electrical energy. That means that here we have some waste. So if I try to fill up this figure over here, let's say now this was 10 joule was lost over here. So let's say the actual heat energy that is actually fed to the turbine is, let's say, only 90 joule. And let's say the turbine could absorb some of this energy, and let's say in the turbine this could actually properly handle some part, and the output stream actually took away some part. So let's say out of this 90 joule, the output stream took away, let's say, 30 joule. So I'm just assuming that the turbine could actually utilize 60 joule of energy. So turbine is only able to encapsulate or extract out from the hot steam only 60 joule, because 30 joule is being wasted. And there is be another source of waste that is also very important. You have to understand one thing: in the boiler there was a moving part. It's a cooking pot. You are blowing heat from the bottom and steam is going up. There is no physically moving part. But the turbine is essentially made with turbine blades, and there is a shaft which is going to rotate. Whenever there is rotating parts, there is friction. Friction produces heat and sound, which is something that we don't want to have. We can use lubrication, we can use graphite and other solid or liquid lubrication to make the friction go low, so that it would not produce that much heat. We can make it small, but we cannot make it zero. So let's say in this process also, due to friction, we're gonna lose, let's say, another 5 joule of energy, which means altogether from this 90 joule, 35 joule of energy is being non-useful. 30 joule is taken off by the hot steam, 5 joule is wasted as friction. So how much energy is actually being absorbed by the turbine? 90 minus 35 gives you 55. So this turbine is able to provide a kinetic energy input to the generator as 55 joule. These are not realistic values, but I'm trying to give you some idea that how does efficiency actually work. Now comes the idea that if we are now trying to convert this 55 joule of energy into the generator, would we be able to produce 55 joule of electrical energy? That answer is also a solid no, because of two things. First of all, inside the generator there is a shaft, there is a coil, sorry, which undergoes some rotation. So there is moving parts, there is friction, so you'll have some heat loss. Goes without saying. The other reason is what we call the Lenz's law. Now, Lenz's law is a bit difficult concept for me to make sense in a short discussion. It's not very difficult, but it's difficult to make sense in short discussion, which I don't want to do because it is included in your electromagnetism chapter, electromagnetic induction chapter in the O-level syllabus. So large discussion about Lenz's law will show up in its appropriate time. But what I want you to understand that, but because of Lenz's law, in the process of electrical of other form of energy converted to electrical energy, or what we call electromagnetic induction, it will always by default lose some energy. The process itself is like that. For example, if I want to give you some example, let's say তোমরা বাকরখানি খাইছো কেউ লাইফে?
জি স্যার।
না বাকরখানি?
জি স্যার।
জি স্যার।
Okay. If I give you a বাকরখানি without any plate and ask you যে তুমি এখান থেকে এক মলিকুল বাকরখানি ওয়েস্ট করতে পারবে না, 100 খাইতে হবে, এটা কি পসিবল অ্যাচিভ করা? Without any plate. You don't have any
No,
plate.
sir.
You have only your hands. You cannot do that.
Nah.
Because bakarkhani is such a snack. The moment you put a bite, no matter in what orientation you do, some things will always be crumbs in so small that it's gonna fall apart. is not going to break like a biscuit or like a toast biscuit. It will make very small crumbs. So the reason I'm telling you that Bakakhani is that kind of a food that you cannot eat without wasting. Converting non-elliptical form of energy into elliptical form is such a kind of process that you cannot do without some wasting. So I'm just using the idea of Bakakhani to give you some practical comparison. It's not the same thing, not at all, just to give you a bit context. So in the process of, in the generator, let's say whenever we are feeding 55 joule of kinetic energy into the generator, let's say out of this 55 joule, the generator is wasting, let's say 5 joule of energy. Why did I? Out of this 55 joule, let's say the generator is wasting, let me use a different color. Let's say 5 joule of energy as friction, and maybe because of that process problem, let's say it's gonna waste another 15 joule. So it's gonna waste a total of 20 joule of energy, which means altogether we'll have a total output electrical energy of how much? 55 minus 20 gives you 35 joule. So this is a type of process. This is just theoretical values. Figure values are not given to scale, or not actual proportional values. But what I really wanted to understand that we started our process. Thank you. We started our process with 100 joule of chemical energy. Kharach hote, after a lot of waste, eventually we could only convert it into 35 joule of electrical energy, which means that this entire process or this entire plant is only 35 divided by 100 into 100%, which basically is 35%. This entire plant is 35% efficient. We can try to find out the individual efficiency of the components as well. For example, if you want to consider the efficiency of the boiler took in 100 joule, gave output 90 joule. So the efficiency of the boiler would be 90 by 100 into 100%. Whatever that is basically 90%. If you consider for the turbine took in 90 joule, gave output of 55 joule. So the efficiency of the turbine would be 55, which is the useful output from the turbine, divided by the total input, which is 90, into 100%. This is the individual or personal efficiency of the turbine. Then if you want to calculate the exclusive efficiency of the generator, that would be 35 divided by 55 into 100%, whatever that is. So each of the components can have their individual efficiencies, but the overall efficiency or the total efficiency, sometimes also use that two words, overall or total. The overall efficiency of this whole process is initial input and the ratio of the final output divided by the initial input into 100%, whatever that is. So this is pretty important, that we want to minimize these losses. The better we can minimize these losses, the more efficient the process can be. And one of the practical ways to minimize the loss or to increase the efficiency is to obliterate number of processes. As you can see, in this electricity generation process, we had a lot of conversions: chemical to heat, heat to kinetic, kinetic to electrical. We had 3 sets of equipments solely purpose for this whole conversion process. But what if we could directly convert heat into electrical? Or if there was a way that we could directly convert chemical into electrical, if it could be happening, if we could somehow discard these whole things, if this whole thing could be achieved in one single step, then it would be easier for us to have a much higher efficiency. So this is a very important idea. Efficiency concept জন্য আমি আরেকটা एग्जांपल স্টুডেন্টদেরকে সবসময় বলি, যেটা আমি অবশ্যই যেটা আমি তোমাদেরকে বলবো, সেটা হচ্ছে the idea of useful output is something that is relative from purpose to purpose, example to example. Let me give you a very simple example which should be easy for you to grasp and you can understand. You kids have seen the filament lamps, which is the yellow lamps which produce a lot of heat and light as well. The filament lamps, you kids know, that has a single wire at the center, not the fluorescent, not the energy lamps, the filament lamps. বলবান তোমার filament lamp চিনো সবাই?
জি স্যার, ওই হলুদ কালার না স্যার?
হ্যাঁ, হলুদ কালার. Still, just to make sure that everyone knows what I'm talking about, I'm just gonna show you one picture of the filament lamp. These are the filament lamps. These are actually more beautiful filament lamps. This is the most common type of filament lamps that we have access in our country. Yes, these two strong wires are the ones that supply the electricity, and this thing that is longed, or this part, this is the part that actually glows. So when it undergoes glowing, this filament glows. Do we have a figure of a normal filament? These are all very beautiful filament lamps. Well, yeah, sure, why not? This one looks a bit like Nixie tube. Do you guys know what a Nixie tube is? Anyone?
No, sir.
You should look it up. Nixie tubes are beautiful. No, apparently I cannot see a regular. Okay, yeah. These are the low voltage filament lamps where the filaments are oriented in a very special design, and whenever you allow it to flow in a certain way, you can have it flowing like this. And these knobs, by rotating these knobs, you can actually increase or decrease the brightness of these lamps. These lamps are actually decorative. They are not essentially useful. They are decorative, so they make stuffs beautiful. Anyway, my point is, filament lamps are such kind of lamps that will simultaneously produce a significant amount of light and heat. It will not produce exclusively heat, it will not produce exclusively light, it will produce both of them. So the efficiency of a filament lamp is highly dependent on what you want from it. Let's consider a simple example. Let's say a filament lamp that has a rated power of 100 watt. Rated power means on the body of the filament lamp, it is written 100 watt. It means every second, watt is the watt, W, capital W, watt is the unit of power. 1 watt means 1 joule per second. 100 watt means 100 joule per second. Whenever a device is labeled by 100 watt, it means that every second this filament lamp will pull 100 joule of electrical energy from the supply line. So it will consume 100 joule of electrical energy per second. So what means it? What means 1 joule per second? Joule per second. I might as well rub this off. What means joule per second? 100 watt means 100 joule per second. So let's say, just for the sake of argument, let's say this filament lamp, out of this 100 joule of electrical input, let's say it produces 35 joule light and it produces 65 joule heat. Let's consider this scenario. These two are the output. That's why I'm showing them with simultaneous arrows, not arrow. Two arrows coming up. So so we can use a filament lamp for many different occasions. So let me give you 3 different examples. Let's say if you use this filament lamp as a reading lamp in your study table, reading lamp. For that operation, your expected form of energy is the light energy. Heat is not your expected form of energy, which means if you're using it as a light source, all the heat that is generated is waste, unexpected form, non-useful form. All the light that is produced is the useful form. It means as a light source, this filament lamp is 35% efficient, because 35 divided by 100 into 100%, 35% efficient. Case 1. Case 2, if you have a hatching machine. Do you guys know what a hatching machine is? It has a good name, I think.
ওই যে একটা ফ্রিজের মতো না?
দাঁড়াও, এটা একটা ভালো নাম আছে। হ্যাচারি না, হ্যাচারি তো হচ্ছে মাছের জন্য বলে। এগ hatching machine. Incubator, exactly. Incubator is the name. I forgot the name. Yeah. Incubator is not a cooking device. It's a conversion device. I mean, it doesn't boil an egg, it converts the egg into chicken. So what happens, is that if you have an incubator, think about it. Let's say you have a tray of eggs that you want to incubate and eventually make chicken out of them. So you have to heat them in a moderate temperature over a duration of time within which the egg will eventually convert into chicken inside the shell. So if you want to use these electrical bulbs, these same electrical bulbs, filament lamps, as the heat source for your incubator, your expected form or required form of energy is the heat energy. You do not need the light energy because the eggs would not need light energy to hatch. They do not need the light energy, which means if you use these exact lamps as your heat source in an incubator, if you wonder why should someone use light sources for incubator, well, the reason is electrical energy is very available to us, point one. Point two, it is very easy to control the temperature of the exact location of the eggs by using light sources. You can have manual regulator like the fan regulators. You can increase or decrease the brightness of this thing to give defined level of heat. Or if you don't even have those devices of regulator, you can bring the light closer to the eggs or take it farther away from the eggs to make the temperature hot or cold or warm, vice versa. So it's easier to control a very what can I say, critical limit of temperature. If you have electrical source of heating, it's easier to control that, which is pretty important for success. So if we use these same filament lamps for a heating source, these are going to be 65% efficient. The third example where both of the forms of this energy might be useful is in the bakery shops. If you have been in a bakery shop where they produce gourmet cookies, you'll see that they have glass jars or glass containers inside which they have their individual cookies, and they use filament lamps on top of those cookies, and they serve two purposes. First of all, they make those biscuits widely visible to all the customers, so which means they need that light energy, and the heat of those light bulbs keep those cookies crispy, dry, non-hydrated. So for that exclusive example, in a cookie shop or in a bakery shop, you would expect both the availability of the energy. You want the filament lamps light energy for good display. You want the filament lamps heat energy to keep your cookies dry. So in that case, in that exclusive case, both of these energies, both of these energies are your useful form. So for that purpose, that filament lamp can be said to be 100% efficient because you want both of them. So both of the forms are your useful output form. But whenever you are using it as a light source, it's only 35% efficient. Whenever you are using it as a heat source, it's only 65% efficient. So my point being, in most cases or in most processes, the process is not 100% efficient because we usually have quite a good amount of byproduct out of devices. Brings us to the idea that heat is pretty much always the most common byproduct of any type of energy conversion. Heat energy is most common byproduct of any type of energy conversion. So you want to convert energy from X to energy from Y, whatever that is. In most cases, heat will be a default byproduct, whether you want it or not. For example, I'm making sound by vibrating my voice. So this vibration, that is actually the sound energy, what is the end fate of this sound energy? Let's say I'm making a sound, or I'm continuously talking. So I'm continuously vibrating the air molecules. What is ultimately happening to this energy? Where is this energy going? Is it getting destroyed? What do you think? Anyone? Did you hear my question, kids? Hello?
So we heard the question.
Okay, so I asked a question that, let's say the sound that I'm making in the atmosphere for having this lecture. So what is happening to the sound energy once they are dissipating out of my mouth and they're not anymore audible? So is this sound energy that I just made, Is it getting destroyed, or is it getting, what is happening to it?
Wasted of his heat.
So wasted as a heat. So what is the medium that is holding that heat?
Air.
Atmosphere. Beautiful. That's what I'm, air. That's essentially what I was trying to get at, that I'm making this sound. It is available / useful for me for a small duration as long as the vibration is alive. But as the sound keeps on traveling, eventually these vibrations are hitting the walls or other parts, or if there is nothing, it is just getting dissipated into the atmosphere. It is getting spreading out, and eventually it is raising the temperature of the atmosphere a little bit because it is the heat energy. So it's getting there. So my expected form was sound, vibration, but ultimately it is converting into heat energy. It's just a very small and tiny example, but the point I was trying to give is that heat energy is the most common byproduct of any type of energy conversion, no matter what you think. This means, interestingly, that electrical heaters can be 100% efficient. Think about it. Electrical heaters can be theoretically 100% efficient. Do you agree?
So can you repeat again?
Electrical heaters, the purpose of those devices to produce
Sir,
heat.
agree.
Electrical heaters can be theoretically 100% efficient because we use them to produce heat. So heat is the output from expected. So they pretty much can convert all of the electrical input as heat energy. So theoretically, they can be 100% efficient. The reason I'm using this term theoretically continuously, I have a reason for this. I could have said that electrical heaters are 100% efficient, period. But I'm not saying that. I'm saying that electrical heaters can be theoretically 100% efficient. Why? Why this set of words?
So
It's
can't there
because,
be any resistive force in the wires?
well, there are resistive forces in the wire, and it is that resistance that converts the electrical energy into heat energy. I mean, the electrical energy converts into heat energy because of the resistance of the coil, whatever that coil is. But still, I'm using the term that it can be theoretically 100% efficient. There is a reason for this. The reason is the energy conversion process can be 100% efficient. I mean, electrical form, arrow, heat energy form. 100% efficient, question mark? Yes. But the overall conversion process can never be 100% efficient. I'll tell you what I mean. Let's say using an electrical heater, you want to heat something. What do you want to heat? Some water, let's say. If you have a basic water heater, you cannot exclusively heat the water. You have to heat up the cooking pot as well, which means you cannot transfer all the heat energy into water, which means you're going to have waste. Forget about water. Let's say we have a room heater. We are going to feed it electrical energy, coils are going to get hot, and it's going to heat up our room. Beautiful. You want the room to be hot for what reason? For your comfort, right? Think about it. Let's say you're a person inside a room and you want the room to be hot. Why? For your comfort, which means you practically need only the air molecules which are touching your skin to be hot. Do you need the entire atmosphere inside the house to be hot? Think. Is it essential that all the molecules of the atmosphere inside the house, inside that room, should be hot? Is it necessary?
No.
You practically need, or you exclusively need, the air molecules which are covering your skin to be hot, and that would be good enough for you to feel comfortable. But can you do that? The answer is no. If you're trying to heat up the room, you have to heat up the entire room, and that includes the atmosphere of the room, all the stuff that is inside the room. If there is your pet or anything else inside the room, if you have an aquarium of fish, that water, those fish, everything inside the room will be heated up, which means you are not essentially, you might as well be producing heat energy, 100% heat energy out of the electrical energy, but you could not transfer the heat energy that you just produced to the exact places you are aiming to go, aiming for it to go. It will always be diverted to some other places. The point that I'm trying to make, that it is very difficult to make a process truly 100% efficient, or increasing the efficiency of a process is actually a difficult job if you think minutely. Why am I telling you this? I'm telling you this because anytime you try to think about increasing the efficiency of a process, you might as well become, very good engineers in the future, or very good scientists or physicists, or anything in the future. Might as well be a business person. So efficiency is very important, that how much benefit or how much value can you make out of limited resources by wasting the least. That's really, really, really important. And another part, another decision that is important that I would like to carry out in today's class, we have about 12 minutes. So yeah, is that except for nuclear energy and geothermal energy, these are the two exclusive types. Except for nuclear energy and geothermal energy, all other energy resources that we have can be attributed to the sun. I'll say this statement again. Except for nuclear energy and geothermal energy, all the other energy resources, renewable or non-renewable, doesn't matter, all the other energy resources can be attributed from the sun. Attributed সাথে কি from হয় নাকি to হয়? What is the appropriate preposition for attribute?
It's 2.
Attributed to. Attributed I believe you, but I just want to check. To set as a source or user something, a noun or pronoun can be used between attribute and to. Oh, yes, thank you. I think it was Nuren. Was it Nuren?
Yes.
Nuren, thank you. So yeah, attributed to. So all the other, except for these two type, nuclear and geothermal, all the other energy forms that we have can be attributed to sun, renewable or non-renewable, doesn't matter. And I'm going to give you some example, but I would like you to practice this example for other relevant. তোমার ফোন আসছিল ছোটটা. I want you guys to practice this example for other relevant cases. Let me elaborate what I mean. Try to think about it. Let's say okay, my fan off করে দেন না আমার আম্মা এই fan off করে দেন. So let's say how can I put this? Okay, we will produce some electricity from a hydroelectric power plant. Hydroelectric power plant means that we're going to have a high reservoir of water in the flow path of a river by creating a dam in the flow of water, and then we're going to allow that high located water through some pipe to fall through. In the following process is going to convert, GP converts to K. K would be fed to the turbine will rotate the generator, and the generator will be producing electrical energy. This is a very, very basic pathway. So if I tell you that a hydroelectric power plant converts the GP of the water into electrical energy, and this is a renewable source, which means as long as, renewable resource, the definition of renewable resource is that this energy source will never run out, which means we're going to have this energy source giving us energy for the foreseeable future, infinite duration, for example, for the foreseeable future. Now, why should we have continuous energy flow out of it? Because we just say that energy is indestructible or non-creatable. We cannot create or destroy energy. It can be converted to one form to another form, or can go from one place to another place. So why is a hydroelectric power plant a renewable energy resource? Why? You have to see the bigger picture here. You have to understand the bigger picture here. What do I mean by the bigger picture is that, think about it. The reason a hydroelectric power plant is defined to be a renewable resource is because this energy or GP supply that we're going to have because of the water stored in the behind the dam is going to be available to us for always. So we're going to always have access to this water. We're always going to have access to this water, which means even though we are continuously draining the water from the reservoir, this water is going to keep filling up because of the flow of the river. Why the river is having its flow? Where is the flow of the river coming from? Now we have to go slowly backwards. Think about it. Any river flow happens from, the water flow happens from a high ground to low ground, which means if a river is actually carrying water, there is a water source located high above, which means let's say mountains or some lake in the mountains, or there are mountains. So from the mountains, we are having the water coming up. So how did the water reach to the mountain in the first place? That answer is the way high mountains receive those water is by means of the cloud. The clouds actually supply the water onto the mountain range by either in three forms. They can be either in the form of rain, liquid, or it can be snow, solid, fluffy solid, or it can be hail. Hails are a bit rare, but it also hails in some places in the world as well. Hails are solid chunks of ice. তোমরা হেল দেখছো সবাই? বাংলাদেশে অনেক বড় হয় না, ছোট ছোট হয়, but still, anyone seen it? Like শিলাবৃষ্টি?
কি স্যার? ও হ্যাঁ 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 দেখেছি।
Yes, small chunks of ice falling. It's very dangerous. It can be very, very dangerous because the velocity of these particles are pretty large. Although it doesn't look like it, but they're usually quite very strong. The hail ice is usually quite very strong because they are formed in atmospherical environment. I mean, their construction process is pretty interesting. The point that I'm trying to get at is that the clouds deliver this water onto the mountain range in the form of rain or hail or snow. So how did the cloud get this water in the first place? So clouds are formed because of the humidity that is present in the atmosphere. How does the atmosphere get the humidity? That's where the sun comes in. The heat energy received by the water bodies of the lower ground or lake or river or other places produces evaporation. Important term, evaporation. These evaporated water molecules and the hot atmosphere, because it is hot, it is light, rise in the upper level of the atmosphere and they convert into clouds. Because of the uneven heating of the sun, a uneven heating conceptটাকে সেটা আমি তোমাদের নেক্সট ক্লাসে বলবো যে why do we have airflow on earth? I mean, why air flows? I mean, why do we have wind? We have wind / airflow on earth's surface because of the sun. How does that happen? এটা আমি নেক্সট ক্লাসে ডিসকাস করে বলবো. So whenever the humid air rise up, it produces cloud, and because of the airflow, which is also attributed to the sun, because of airflow, these clouds are pushed to the up higher level in the ground, on land, and that's how and when these clouds produce the rain or hail or snow, those water which are evaporated from lower level of land, of lakes or rivers or ponds or oceans, other places, this water is practically delivered to the higher level of the mountains. So basically speaking, the heating of the sun is basically working like a huge water pump. But this water pump is not like a regular water pump, like electrical pump pumping through its water through a pipe. No, the heating of the sun is working like a water pump through the huge channel of the atmosphere. It is evaporating water, so the atmosphere is becoming, it is starting to take in the water molecules, and it is converting into air, into clouds in the high level of the atmosphere. Those clouds are pushed into the land because of the airflow, and that's where those water is falling down. So basically, there is a huge amount of water flow happening from the surface of the water bodies, oceans and lakes and rivers and other places, seas and other places, and these are pushed all the way to the mountaintops. And that from there, after the water falls down in the form of rain or hail or snow, that water flows to the river. So you have to understand that as long as the sun keeps giving the heat energy, this evaporation will keep on happening, and wind will exist, and the clouds will form, and the rain slash hail or snow will happen, and water is always going to flow downstream from the mountain towards the lower level of the land. This cycle, I practically described you the water cycle. This cycle is essentially what makes a hydroelectric power plant renewable. If sun stops giving us heat somehow, then this will not happen. Water will not be evaporated and not be pushed to the mountaintop, which means then the remaining water in the atmosphere will be flowing down the river, and the river will eventually become dry because the mountains will not be receiving continuous supply of water in the form of cloud. And if they don't receive water, the rivers would not be alive anymore. The only reason the rivers bring down water is because they are delivered or supplied with the water in the form of cloud. So it is the sun that actually causes the whole thing to work. So the GP that we actually get in the dam is practically the heat energy from the sun, which was stored in the water molecules when they become evaporated and rose up in the upper level of the atmosphere. Have a look. We are converting the GP stored of the water molecules into kinetic energy to electrical energy in the process of hydroelectric power conversion. So how did this water molecule get this GP in the first place? Try to understand. These water molecules, think about one water molecule at the ocean level. Sun's rays are falling, it is getting evaporated from the surface, it is starting to rise up as hot air rises up in the atmosphere, and it reaches, let's say, 10, 12 kilometers in the atmosphere. That's exactly when this water molecule gained its GP. It would then from the cloud maintain its GP, flow onto the land, still maintain its GP, then it's going to lose some GP as it's going to fall onto the ground in the form of rain or hail or snow. And then as it's going to fall down through the rivers, it's going to continuously lose its GP. By producing that dam in the path of a river, we stored that GP for a small duration. So we are practically using a small fraction of energy that the sun actually gave to each of these water molecules. We are not even using all of it, a very small fraction, because sun practically lifted up all of these water molecules from the ocean level to the atmospheric level where clouds were formed. That's a huge amount of energy that we're talking about. And we can only use a very small fraction of this energy. Point being made is that the energy that these water molecules have were initially given from the sun. এই এক্সাম্পলটা কি বুঝা গেছে কিনা? Kids.
জি স্যার, বোঝা গেছে।
Anyone else? Any questions so far? If you have any question, just respond. Ghulam Mustaqim asked me a question which showed up in the private chat in the Zoom window. He asked me that, what about the magnetic energy? Well, one thing that I would like to tell you is that there is practically no form as magnetic energy. Magnetism is an exhibit property of certain substances. The reason the exhibit property of magnetism is actually an output of moving charges. So magnetism is a very closely associated phenomenon with electricity. So magnetic energy doesn't exist, electrical energy exists, and flow of electricity shows as magnetic behavior. Do I make sense? যেমন, for example, Mustaqim, one thing I can try to elaborate. For example, let's say exclusively খাসির হাড্ডি এক্সিস্ট করে না, কাচ্চি এক্সিস্ট করে বলে খাসির হাড্ডি তৈরি হয়। Does it make sense?
No.
I mean, when you eat, I mean, I just said that exclusively khashir haddi exists. I mean, they just don't pop in random places. Because kachi exists, khashir haddi is produced. So we eat those kachi, we eat the meat and the rice, and because we don't eat the bones, that's why they are coming out as an output. So magnetism is sort of like the byproduct of electricity. Magnetism itself is not a thing that is a sole existence of its own. বুঝছো কি বলছে?
স্যার আবার বলবেন?
It's a weird example, right? It's a very weird example. মানে হচ্ছে যে magnetic, I mean, the question that Ghulam Mustaqim just asked me, that what about magnetic energy? Because I just said that apart from nuclear and geothermal energy, all the other energies can be attributed to sun. That's what I say. So I believe in that context, he asked me that, what about magnetic energy? The response that I'm making is that there is no such thing as magnetic energy. Magnetic force is present. The reason we experience the magnetic behavior of certain objects is because of flow of charge. It is the movement of charges that give objects the behavior of magnetism. Magnetism is not a sole behavior. It is an associated outcome of something. বুঝছো কি? মোস্তাকিম, তুমি কি বুঝছো আমি কি বলছি?
স্যার বেশি ভালো করে বুঝি নাই।
How can I make it easier to understand? মনে করো, let's say heat energy flows from hot temperature to cold temperature. আমি যদি দুটো অবজেক্টের মধ্যে হিট এনার্জি ফ্লো করতে চাই, তাহলে আমাকে জাস্ট টেম্পারেচার ইজ দ্য only variable that I have to maintain. One object has to be thermally hot, another object has to be thermally cooler, and if you contact them or allow them to transfer heat between each other, hot object is going to lose heat energy and cold object is going to gain heat energy. That's how it's going to happen. So the only variable that is going to control the behavior of heat energy flow is temperature. Temperature difference exists means heat energy flow is going to happen. Cause and effect. Now, in the similar perspective, the flow of electrical energy happens because of voltage or potential difference. So whenever there is excess electrons in an object, or whenever there is shortage of electron in another object, if you connect them together, electrons are going to flow from the excess location to their shortage location to minimize the imbalance. That flow of charged particles is essentially what we define as electrical energy transfer. Whenever electrical energy transfer happens, that additionally produces the magnetic behavior. Magnetism itself is not shown as an unique property. Now you might wonder, then How about permanent magnets? So if we have permanent magnets which give us the magnetic behavior, does it mean that there is always flowing charges within itself? That answer is yes and no. It is yes because it is the flow of charge that shows magnetism, so it has to have some flow, some sort of flowing charges. And no, because these particles which actually flow or move to show us the magnetic behavior of a permanent magnet or a bar magnet, for example, they are subatomic particles that happens at the quantum level. So I'm using yes and no because I have to say yes because that's the reason. I am trying to say no because I do not have the knowledge or the know-how to make it understandably explain it, to explain it at an understandable level to you, that why magnetism exists. বুঝা গেছে? That's the best I can do to explain magnetism. Magnetism is in theory is actually, magnetism is pretty cool to observe, but its explanation is a bit complicated if I really want to get to the bottom of it. Anyway, listen up, kids. We are a bit above our regular time, and one person has already left, and I don't blame them. We're gonna pick up the discussion of work energy per chapter from this point inshallah next class, and we should be able to pick up some worksheet problems as well. So thank you very much. Allah Hafiz.
Allah Hafiz, sir.